Alright guys, so I'm going to make another video here. It's been a while, but school is in session, so I've been very busy with that. But I'm going to make another video right now. This is problem 8.3 out of John Taylor's Classical Mechanics textbook. So I'm going to go ahead and do this, and if you wouldn't mind please liking the video and subscribing. It does motivate me to post more, so if you could do that, I would greatly appreciate it. Okay, so we have two particles, mass m1, m2, which I have drawn there, are joined by a massless spring, which you can see, of natural length L and force constant K. Initially, m2 is at rest at the table, and I am holding m1 vertically above m2 at a height L. So hopefully that kind of makes sense with the picture. At time t equals 0, I project m1 vertically upwards with an initial velocity v0. Find the position of the two masses at any subsequent time t and describe the motion. Okay, so this looks like an intimidating problem, but it's not too bad. It's actually quite fun, actually. So the main equation we're going to use, and we're not going to touch on this right away, but I'll kind of write it out so you know where we're going, is this equation. Okay? So, and I'll draw a diagram so you know what all these values mean, but this is an equation out of the Taylor textbook. It's not hard to derive, and maybe I'll do it in one video. So I'm going to just draw a little picture. I don't know, we'll call this M1, M2. We'll call this the origin. So pretty simply, this is vector R2. This is vector R1. So right away, you can see this is what we want to find. R1 and R2. Since those are the position vectors from our origin. Now, we're going to need to know this vector, r, which is just r1 minus r2. Okay? So that is in our equation. And then big R, so let's say, just for an example, the center of mass is right here. Let's say that's the center of mass. Big R is the vector from the origin to that position where the center of mass is. Obviously that shows up in our equation there, so it'll be necessary. Okay, so that's kind of our setup here. Hopefully that all makes sense. And we're going to start with writing down the Lagrangian for this system. So the Lagrangian, and this is worked out in the textbook here, is the Lagrangian for the center of mass and the relative Lagrangian. Essentially, you're treating this as two separate systems in a way, one with the center of mass and one with the reduced mass. So if I think just about the center of mass, well, it's going to have a kinetic energy 1/2 mr dot squared, because as you throw this spring up, the center of mass, wherever it is going to be moving. So it's going to have some kinetic energy, and the potential energy, we'll just say mgr, since that's the distance from the origin to the center of mass. That's like your height. The total mass, m, and then of course g, the gravitational constant. So that's for the center of mass. And we need to add to that the Lagrangian relative, which is treating it as a reduced mass. And for the reduced mass, well, that's also going to be moving. So we'll do 1/2 mu r dot squared. So the center of mass is moving, the reduced mass moving. And then as for the potential energy, well, it's a spring. And the potential energy for a spring is 1/2 k. And then basically the displacement from the natural length, so we'll say r minus L squared. So the r is the distance between them, and we're subtracting off that the natural length L. And that's the potential energy for the spring. Okay? So hopefully that all makes sense. This is your Lagrangian. And now what we can do is we can use our Lagrangian here to solve, to generate some differential equations, which will, once we solve, will explain the motion. So the first one is we'll use the Euler Lagrangian here. The partial derivative of L with respect to big R is the time derivative of the partial derivative of L with respect to R dot. Okay, so there's only one R, so that's quite easy to take the derivative of. That's going to be minus mg. And we're going to be taking the time derivative. If we do the derivative of L with respect to R dot, that's only right there. That'll be m R dot. So you get minus mg equals m R double dot. Okay. And obviously we can divide out the m's, and we get the differential equation R double dot equals minus g. And this is actually a pretty easy differential equation to solve. We can see R dot of t. I guess it's not really a function of time, but you know. We can just integrate this. This is separable. Minus gt plus, I'll say v naught cm. So that's just your initial condition. You can call it whatever, but I'll just say the initial velocity for the center of mass. And again, this is separable, so 1/2 minus gt squared plus v cmt plus, I'm going to call it r naught. Okay, so this is pretty good, but this is a general solution. We can get a particular solution using our initial values, starting with the fact that we know r of 0, well, r of 0 is just going to be r naught. And if we think about r, so r is just the center of mass vector. That is m1 r1 plus m2 r2 over the total mass, right? And that's the definition of center of mass. And the way that I define my coordinate system here as y0 being where mass 2 is, this is just 0 because r2 is at the origin. So r naught is going to be just m1L over big M. And remember, r1 is a height L above. So r1, the distance from the origin to mass 1, is just L. So, okay. One of those constants that we didn't really know, we now know what it is. Okay. And likewise, if we take the derivative of this, r dot is going to be just m1 r1 dot plus m2 r2 dot over m, or, of course, m1 v naught over big M. So initially, the only thing that has your velocity here is the mass 1. Mass 1's what's being thrown vertically upwards. After some time t, everything's going to be moving, mass 1, mass 2, the center of mass, the reduced mass. But initially, we're only giving mass 1 a velocity. So this is, once again, 0. So that's important because this is r dot at 0 is equal to that. And if we plug that into here, right, we can see that v naught for the center of mass, obviously that goes away. You'll have, this is going to be just 0. at time equals 0. V naught over big M. Okay. So now we're going to put all this into a final equation, R of t minus 1/2 gt squared plus m1 v naught over big M t plus m1 L over big M. Okay. So we have this, and this is necessary because we can see R comes up here. And what is this telling us? Well, essentially, if you give us some time, I can tell you where the center of mass of this system is, which is pretty cool. That's actually quite impressive. So at some time t, you know where the center of mass is. But that was just one of the two differential equations we could solve for with the Euler Lagrangian. So we did with respect to r, we could have also done little r. We did big R, but now we can do little r. So we can do the Euler Lagrangian again, but this time replacing big R with little r, and we'll get a different differential equation that will describe the separation between mass 1 and mass 2. Okay? So we need to take the derivative of the Lagrangian with respect to r, right? So coming over here, just a little chain rule. You'll get minus k, r minus L, equals d by dt. And if you take the derivative with respect to r dot, this is the only guy there, you'll just get mu r dot. And taking the time derivative of that, we yield this differential equation. And this one is a little different from the last one. It takes a little bit more work to solve, but it's not too bad. First thing I'm going to do is I'm going to divide over by mu, and then I'm going to define omega as the square root of k over mu, which is pretty normal whenever we have a spring. Usually it's k over m, but our mass is the reduced mass in this case. So now we have r double dot equals minus omega squared r minus L. And then I could distribute that, and I get r double dot equals minus omega squared r plus omega squared L. And finally I can rewrite it as this, r double dot plus omega squared r equals omega squared L. So how do you solve this differential equation? Well, it's in the form a1 y, I'll just call it y, double prime plus a2 y prime plus a3 y equals some constant c. That's the form we have it in. And to solve this, we essentially need to do, I'll just say, we'll call it x. We need to solve the homogeneous equation first, and then we need to add to that the driven value, which is actually pretty easy. So the driven value, we'll actually do that first because it's so easy. The driven value is, you take your constant, which in this case we have c is omega squared L, and then you divide by it the term that's with your just y term. So essentially it'll be, in general, c over a3, and for us, omega squared L over omega squared. Obviously this is just 1, so this term is just L. So that is that part. Next we want to solve the homogeneous part. So the way that we do that is we basically pretend that there is no constant term. So we set this equal to 0. And the way that you solve this one is you just solve the characteristic equation. So we have lambda squared plus 0 lambda, since we have no r dot term, plus omega squared is equal to 0. And we want to solve for lambda, so lambda squared is minus omega squared, or lambda is plus or minus I omega. And this is obviously complex. So whenever you have complex roots, the solution to your differential equation will be in this form. So the real part in this case is 0. There is no real part, so that's going to be just 1 times a sine of, you take your imaginary part, so omega t, plus b cosine omega t. And this, I should say, is for the homogeneous part. So now our general solution to this differential equation will be a linear combination of what we just found. So a sine omega t plus b cosine omega t, and then plus the L we found earlier. So now, just like before, we want to take the general solution and make a particular solution. So r of 0 initially is a distance L. It mentions that in the problem, that he holds the mass to a distance at a height L. Okay. So initially that's how far apart they are. And if we plug in 0, well, that's going to be just 0. So we'll just have b plus L, since cosine of 0 is 1. So 0 equals b. So this term we actually don't have to worry about. So now we have r of t equals a sine omega t plus L. So now we just need to find our constant a, and we can do that by taking the derivative to get a omega cosine omega t, and then of course the derivative of L is just 0. Okay? And we set this equal to v naught. Well, we will when we do r dot of 0. So we'll just have a omega equals v naught, or a equals v naught over omega. And then finally, r of t is just going to be subbing in our a, v naught over omega, sine of omega t plus L. And now, with all this, we can find R1, which is the position. That's just R plus M2 over big M R, right? And we solve for all this, so we have big R minus 1/2 g t squared plus M1 v naught over big M times t plus M1L over big M. So that's big R. And we have this factor M2 over big M R. It's just plugging in what we just found. And you can distribute what you'll have is minus 1/2 gt squared plus m1 v naught over big MT. And then notice, so I'll go ahead and actually do m2 v naught over big M omega sine omega t. If you factor the L out, you'll have m1 plus m2 over m, but remember big M is the total mass. So this is just 1. And then R2 is the exact same thing, only it's minus m1 over mr. So you get minus 1/2 gt squared plus m1 v naught over big M t plus m1 L over big M minus m1 over big M v naught omega sine of omega t plus L. And this time, if you distribute, you'll notice that this term and this term will cancel. So it's just minus 1/2 gt squared plus m1 v naught over big M t minus m1 v naught over big M v naught sine omega t. Okay? So just to summarize what we did, we had this problem. We drew a little picture. I guess I drew it before I started the video, but that's where we were. We recognized the two equations that would tell us the position of our particles at any time t. We found our Lagrangian of the system. We used the Euler-Lagrangian equations to generate two differential equations. We found the position of the center of mass with respect to time, and we see it acts kind of how we would expect a clump of mass in a gravitational field to react, how would we predict it to be. It's just very similar to a kinematic equation, essentially. And then we did the same thing with R, and we got a different differential equation here. But once you solve that, you get something that's oscillatory in nature. It oscillates, which again makes sense because we're dealing with a spring here. And then once we did that and we found our particular solutions, we plugged them in, and now we have two equations that describe the position at any time t of this system. So hopefully that helped. If it did, please like and subscribe, and I will continue to post.